Good afternoon, everybody. So today I'll be talking about the safe and secure software factory. So for those of you who are old enough, you're probably familiar with one of these systems. It's a Cray supercomputer, and it was created by Seymour Cray. What's really interesting about the quote here is that Seymour Cray made this quote 35 years ago. And the challenges of building software 35 years ago are still very much the same today. And so this is not because developers haven't gotten better, but it's because the systems that we're building have become more and more complicated. It's very similar to thinking of your brand new PC that you have at your desk that has 32 gigabytes of RAM, 8 cores, and Windows 10. And it still seems to run as slow as your old PC, which had Windows 7 and 8 gigabytes of RAM and 2 cores. In the same way, software complexity has grown, and so the challenge and the task of developers has also grown in complexity as well. So if we look at this slide here, so the hockey stick picture that we see here, the cost of defects, is quite a commonly used graph. And it was based on research that was done by Capus Jones, a famous researcher in software quality. And what it basically says here is that the cost of finding and fixing a defect becomes significantly more expensive the later in your software process that you leave it. And so this slide has been used as a justification by a lot of development organizations to try and shift left, to try and identify issues in our systems much earlier in the process at the developer's desk. And there's been really good work that's been done in this area. But one of the challenges is that there are still some things that can only be done in the system build phase, like assembling all the components together. So while we've done a good job of fixing issues earlier in the process, there are still some penalties that we pay when we assemble the system, and all the cost that's associated with trying to root cause and find the issues there. And so what we'll talk about today is how we can minimize the cost of assembling the system and make it easier. So the other aspect is technical debt. So technical debt is basically kind of the problem that doesn't hit you today. It's the problem in your software that slowly evolves over time and erodes away at the quality of your software. Current continuous integration techniques that people are using are good, but they don't prevent this erosion. And so what generally happens here is that a decision that's been made earlier or a change that's been made earlier in the software can eventually manifest itself and causes problems much further down the path in time. And the problem is that it doesn't happen immediately. It might happen months later, it might even happen years later. But eventually what happens is that things stop working, and then we are paying the penalty of the bad decisions that we made much earlier in the process. And so if you think about software IP, I mean, software IP is critical, and if you have high technical debt, it limits your ability to evolve that software IP over time. And this, of course, means that you're very restricted in what can be done. And so this kind of brings us to the emotional cycle of manual delivery. So we kind of have the plateau of obliviousness. So this is the area where we're happily working on our project, things are going well. And so VDC, Venture Development Corporation, who's a researcher in the embedded industry, a couple of years ago said that 66% of embedded projects deliver late. And so very often what happens is that we come to our ship date, we miss the deadline, and then we get into the cliff of urgency. And so this is the area in time in our project where we have to do things that have to be done fast, we take shortcuts, we make compromises in our design, in our decisions, in what we're building to actually ship the software. And then, once it's done, we start to relax and we go back up the thing, we become relaxed and we get really happy, and finally the customers got their deliverable and maybe we've been paid for the work. And then after the peak of jubilation, we start to become complacent again. So we start to make the same mistakes. And this kind of roller coaster ride goes up and down from every project to every project. And so what we want to try and do is minimize this and kind of have some consistency and be generally happy. So some of the causes of this kind of delays can be, sort of root cause to these kind of defects. So the usage of free and open source software. So these are things like someone has used a library that has a license conflict, so it's a GPL library, so it can't be used in our application. Maybe someone has gone on Stack Exchange because they didn't know how to implement something, and they've copied and pasted some code, and that code originates from an open source library, which is GPL'd. Or maybe we've used a library that actually has some vulnerabilities in it, some security vulnerabilities, and our device is going to be an endpoint, or it's going to be on the internet or connected in some way, and that potentially exposes us. Architecture, so maybe the coupling or the cohesion is very poor in the software, and so this affects our build times, right? Security, so maybe there's data leakage, there's a possibility for SQL injections as more and more IoT devices become connected, or even possible remote code execution where someone can take control of our system and run their own software on it, or their own application. Then typical things like threads and deadlocks, so your kind of priority inversion and classic multitasking issues. Interprocedural, so class interfaces, recursion, crashing, null pointer dereferences or buffer overflows, data flows, so uninitialized variables, or maybe unsanitized data usage. Maybe there's a way of providing user input into your system, and the data isn't being checked correctly, and this can take an unexpected path through the software. Control flow, so dead or unreachable code, so even though the code looks correct, actually it's syntactically correct, but it doesn't do what it's expected to do. Semantic, so again, it compiles, the classic statement, my code is correct, it compiles. Yes, it compiles, but it's actually not doing what you probably expect it to do here. Or syntactic, and syntactic is probably one of the easier ones because this is something that compilers can pick up today. And of course, all of this, and we still also have to build software that matches our requirements. So we're at Vector, who's a great supplier to the automotive market. And so what better example than to take one of the leaders in automotive manufacturing, Toyota, and the Toyota production system. So the idea here is that Toyota basically came up with the system to deliver the highest quality products with the lowest cost and the shortest lead time. And it's essentially done on 3 pillars. So the first one is just-in-time. And in particular, one of the things that determines just-in-time is to only have the components that you need to assemble what you need to assemble. And that's done through something called takt time, which is the time between building a unit and being able to start building the next unit. And that's typically matched to what your customer demand is or what your supply demand is. The other area is having a culture of continuous improvement, so finding and fixing problems. And the area that's of interest to us is Judoka. So Judoka kind of introduces this concept of automation, of bringing a human aspect to automation. And the idea here is that it's built on these 4 principles of quality. So the idea is that if you see a problem, halt the production line, investigate it, see if you can fix it, start the process, and then do a root cause analysis to make sure that it doesn't repeat itself. And this kind of process of continuous improvement on the production line and finding and stopping and fixing problems is actually something that's very interesting that we can apply to software. So a way of doing this is using and-on. So if you've ever seen any photos of factories in Japan, you will see like you have the production line and then you see this sort of cord running across the production line. And the idea here is that any time a worker sees an issue, they pull the cord, an alarm sounds, the board flashes up which workstation the issue is, and typically the team leader for that section will come over with the worker and then they'll investigate the issue. If they can't fix it, the alarms keep sounding and then the next level manager comes down. And so the idea is that whenever an issue is seen, the worker is encouraged to pull the cord and they investigate it. And so it's quite common that in a typical shift, the cord might be pulled 12 times, with maybe the production line halted at least once. And so this kind of concept is really interesting because we can think about doing something similar, but applying it to software. So again, the concept of and-on is interesting, but it still requires an aspect of human involvement in the process of analyzing and looking at what's going on and then trying to interpret and make a decision. Of course, as we know with all kind of manual processes, when we're under pressure, when we're in the cliff of urgency, all these kind of manual things get forgotten and we kind of miss them later on. So the idea is that if we're going to do this, it's great, but we need an automated way of doing it. And so this is where we can start thinking about the first thing, which is delivering incrementally. So this is a common agile concept, but it's interesting here. So what we talk about is instead of trying to do a big bang delivery, which results maybe sometimes in a big bang, the idea here is to try and break up the work into smaller work packages and do much more frequent releases. And the benefit of that is that we dramatically reduce the risk. It lets us respond faster if we have changes in requirements, if we identify an issue in the system that we're building, those can be rectified and incorporated in the next release. And very often, releases are made even before there's a minimum viable product. And then the other aspect is that we can have continuous feedback. So we keep analyzing the changes that we're making, ensuring that we're maintaining the high level of quality in the product as we keep iterating over it and doing subsequent releases. So let's apply TPS to software. So bringing the automation process in. So if we think about software, what we want to do is basically implement something that can analyze our software and tell us if things are okay. And we'll call this a software quality gate. And the idea of a software quality gate is that every time a developer does a commit and we want to progress it into the next stage, so into the next level in the branch, we need to run it through a software quality gate and make sure that the delta that's coming in is clean. And so we'll call this each stage TX. And so T0, or time 0, is basically the developer's desk. So this is where the developers actually made the change that they want to commit. And this could be a bug fix, it could be a new feature, it could be a new aspect. And so we call this isolate. So let's isolate the delta, and then let's verify it. Let's take that delta and apply it to the tested software and not include any other untested software in the process. So here we check for things like quality metrics. So is the complexity still good? Is the maintainability metric still good? Are all the test cases passing? We check for all the common root cause issues, so all the things that we discussed before, like the open source compliance, the security checking, all the kind of bugs and failure conditions that we might have. And then also all the deliverables as well. So if we're working in a compliant environment like 26262 or a medical device or avionics, we want to make sure that all the new code that's been added has traceability to requirements, to design, has the appropriate test cases, and so on. And if it doesn't have that, then we don't permit it to progress. And then finally, once it's clean, once it's past the verify stage, then we allow it to merge into the main line. And so the idea here is that at each one of these dots that we see here, we basically are doing a quality gate and making sure things are okay, and this is completely automated. And in this way, we allow a change to progress from a developer's desk into a development branch, or into a feature branch, and then into a development branch, and then into our final release branch. So if you're like my 9-year-old son, you don't like roller coasters, right? Especially the big drops. And so it's a very similar thing here. If we look at this typical kind of release branch here in most projects today, you have areas where the branch is clean and it's green, and you have areas where it's red, where it's broken. And that can be broken for extensive periods of time. And the idea here is that we want to prevent this, because today what we do is we implement a feature, we commit the changes to the repository, and then we merge, and then we test. And so when we introduce the concept of the software quality gate, what we do is that when a commit is made, we run it through the software quality gate, and it's not allowed to progress until things are working well, until all the checkpoints that we have are being met, and then we merge, and then we bring it in. And in this way, the TX+1 branch is always clean. It's always usable. And this is very, very important. So another aspect is we spoke about technical debt before. So some of the other things to think about are in the standard IEC 9126. And so here we talk about things like functionality, reliability, usability, efficiency, maintainability, and portability. And these are all things that can be measured with or analyzed with classic COTS tools. So things like test automation tools, static code analysis tools, and software architecture tools. And we can use this as part of our software quality gate process, again, to measure and make sure that we're maintaining a level of quality in the system for each increment that we're bringing in. So, the software factory approach. So again, what about infrastructure and stack? So all this time, when we build software, we think about building software just as building our own simple application. The challenge, of course, is that it's not that simple. Today, if you're building a system, there are many, many pieces that you need to be able to build a system that you want. So in this example here, you can see for whatever you're building, you might need protocols for your communication, you might need algorithms for your autonomous driving system, and so on. And so the idea here is that when you're building software, you need all these components to be able to make it to work. And the challenge, of course, is that not only do you need to make it work once, you need to make it work on every developer's desk. So it's very common, for example, that you might get a patch or an update, and when you need to make that update to the system, you need to do it in the right order. Otherwise, it works on this desk over here, but it doesn't work on that desk over there, or it doesn't work in the continuous test system, or maybe that configuration is different to what's running in the deployed system. And so the idea here is that let's look at infrastructure as code. So if we look below the dotted line, so this is basically our physical aspect, or maybe our semi-virtualized aspects of things like the hardware, your storage, and your network. And we don't really need to care about that stuff. What's important to us is what's above the line. So this is the actual IP that we're building, the application. It's all of the application infrastructure, the operating system config, and all those different kinds of things. And so the idea here is that for the bottom side, we can bring in some technology to help us here. So we can run with public or private clouds, so things like Azure or Alibaba Cloud or Amazon Web Services, and we can use this to completely virtualize our infrastructure. And then we can run something called containers, so either something like Docker or Kubernetes. And both of these containers allow us to script the construction of our infrastructure. So in this example here, I'm running a particular distribution of Linux. So this is Ubuntu 17. And the idea here is that you can specify the script, and then you can specify exactly what components you need for your environment to be set up correctly. And then every time you need it, you just run the script, and it rebuilds all of the infrastructure for you. And the beautiful thing about this is that you can put this into configuration management. And you can map this with your source code as well. So the configuration for your environment is directly coupled with your source code. And this means that if anyone wants to repeat or retest that software, they can rerun the infrastructure script and create it. And the other aspect as well is that working in this way, if you're going through a peak period of activity and you need to ramp up more infrastructure, you just run the scripts, you create all the infrastructure you need, and then you tear them down. So there's a big cost saving as well of being able to manage the peak load, because you can virtualize things in this way. So this process is basically bringing full automation to the software development lifecycle. So inside each software quality gate, we're doing things like building. So we're making sure that we can always completely build our software. Using the infrastructure as code capability that we spoke about before, we can ramp up as much infrastructure that we want, that we can actually do this fast enough on every commit. We can do testing, so we can rerun all of our unit testing, integration testing, and system testing, bringing concepts like change-based testing, for example, so only testing impacted code, impacted test cases, only rerunning those. We can do static analysis, so looking at things like compliance to MISRA or AUTOSAR C++, and even other quality metrics as well that you might have to do with maintainability or reliability. We can do our security checking. So at time zero at the developer's desk, we can actually run security analysis and scan for known common weakness enumerations in the code and make sure that they don't exist. We can analyze the architecture to make sure that we're not introducing things that would make the architecture more complicated, which might impact the build behavior later on down the line. And then finally, compliance. So using our ALM tools, we can check for traceability and ensure that anything new that's coming in is being measured correctly and is linked correctly. And so here I have a little case study. So this is a Jenkins pipeline that we've built here. And so in this example, we use Jenkins to build a sophisticated pipeline. And the idea was that every time a developer did a commit, we would use it Jenkins would be dispatched to run a software quality gate. So it would take it would run the static analysis on the code. We would then use LaTeX to do the architectural analysis to make sure that the architecture was in a form that was interesting or was acceptable. We would then spin up a Docker container, which we would use for doing the build. So this would have the exact specifications of the build, so we would make sure that the developer hadn't introduced something locally that might not be in the main system. Then we would also spin up a virtual target, so in this case it was QNX. And then using unit testing, we would do parallel unit testing across the whole system. Then we would run white source, which is a tool for doing compliance checking for open source software, so making sure that the libraries that we're using are the right license model. And for the versions of the libraries that we're using, there weren't any known vulnerabilities that were already shipping in the software. And so the really cool thing about that was we were able to reduce building times by 65%, and also reduce broken builds on the development branch by 75%. So huge improvements in the usability of the branches that were available. Quality, we were able to reduce technical debt in the system, and so this had a saving of over $100,000 on this project. We found 45 crash causing defects at the developer's desk at time zero, so before they propagated further into the chain, or before they were even committed into the code. And security vulnerabilities, so using a tool called SEML, we're able to identify more security vulnerabilities earlier in the process. And so this resulted in a 40% reduction in vulnerabilities detected at T3, or time zone 3, which is basically the release branch. So that was a really good success story that we had with the technology. So, thank you.